Hello and good day, everyone. I am Leon Grace S. Ortado, and in this presentation, I will be explaining several important concepts in linear algebra. These topics play a significant role in mathematics and are commonly applied in different fields such as engineering, computer science, physics, robotics, artificial intelligence, and data science. So the concepts that I will cover include the dot, the angle between two vectors, the dot product, the cross product, the linear combination, linearly independent, the linearly dependent, the basis, the spanning set, and the dimension. These ideas are important because they help us understand vector spaces and how vectors are related to one another. They also serve as the foundation for more advanced mathematical studies and practical applications. So these topics here, 1, 2, 3, 4, 5, 6, 7, 8, 9, these 9 topics that we will be discussing is important because it serves as a foundation for more advanced mathematical studies and practical applications, especially also in our daily life. So now I am going to introduce to you to the vectors. We are now in slide 2 as the introduction to vectors. What is vector? So the very first thing that we need to do for us to know the topics, it is first important for us to understand what are vectors. So here a question, what is a vector? A vector is a quantity that contains both magnitude and direction. So when we say magnitude, it refers to length or sides of the vector, while direction indicates where the vector is pointing. This is what makes vectors different from scalars. So in physics, we can differentiate vectors from scalars. Examples of scalars are the displacement, the speed, and etc. While for the vectors, it has magnitude. Like for example, the velocity, the acceleration, and etc. This also is what makes vectors different from scalars again, since scalar quantities only have magnitude and no direction. So that is the difference between a vector and a scalar. Here, vectors are often represented using arrows, here above that letter V, or ordered pairs and components. As an example, the vector angle bracket 2 3 represents a movement of 2 units along the x-axis and 3 units along the y-axis. So this is the example of vector having its 3 components, the v sub 1, the v sub 2, and v sub 3. So vectors are very useful in mathematics and science because they can represent physical quantities such as force, displacement, acceleration, and motion. Understanding vectors is essential because the concepts discussed later are all connected to vector operations and vector spaces. Moving on, we are going to discuss about the angle between two vectors. So the next concept that we are now going to discuss is the angle between two vectors. So the angle between two vectors measures how closely two vectors point in the same direction. To find this angle, we use a formula involving both the product and the magnitude of the vectors. So cos theta equals the, the product of the vector A and vector B all over the magnitude of A times B. The magnitude of a vector refers to its length, of course. When the angle is 0 degrees, the vectors point exactly in the same direction. If the angle is 90 degrees, the vectors are perpendicular or orthogonal vectors. If the angle is 180 degrees, the vectors point in completely opposite direction. This concept, by the way, is important because it helps describe directional relationships between vectors. It is commonly applied in fields such as robotics, navigation, computer graphics, and machine learning. For example, in machine learning, the angle between vectors is often used to determine similarity between data sets. Smaller angles usually mean greater similarity, while larger angles indicates less similarity. So when we say smaller angles, of course, it means greater similarity, and when we say larger angles, it indicates lesser similarity. Next up, we are going to discuss about the dot product. So the dot product is an operation between two vectors that results in a scalar quantity or a single numerical value. To calculate the dot product, we multiply the corresponding entries of the vectors and then add the products together. So when we say if the vector A has component A sub 1, A sub 2, and A sub 3, and then the B has the component B sub 1, B sub 2, and B sub 3, all we just need to do is simply multiply the corresponding components and then add them all together. And that gives us A sub 1 times B sub 1 plus A sub 2 times B sub 2 plus A sub 3 plus B sub 3. So for example, if vector is the angle bracket 1, 2, 3, and vector B is angle bracket 4, 5, 6, we multiply the matching components and add the results from what I've said earlier. This gives us a final answer of 32 here. So since we multiply 1 times 4, that would be 4, 2 times 5 is 10, 3 times 6 is 18, so adding them all together, it gives us 32. So the dot product is useful because it helps identify the relationship between two vectors. It can indicate whether vectors are pointing in similar directions, opposite directions, or are perpendicular. A positive dot product means the vectors generally point in the same direction. A negative result means they point in opposite directions. If the dot product equals 0, the vectors are orthogonal or perpendicular. This concept, the dot product, is widely used in areas such as physics, engineering, machine learning, and computer graphics. It is also important because it is used in determining the angle between vectors. Next up is the cross product. Unlike the dot product, which produces a scalar value, the cross product here, it produces another vector. This operation is only defined in three-dimensional space. So the vector obtained from the cross product is perpendicular to the two original vectors. Meaning to say it forms a 90 degrees. An important property of the cross product is that its magnitude represents the area of the parallelogram formed by the two vectors. The direction of the resulting vector can be determined using the right-hand rule. In this rule, the fingers follow the direction of the first vector and curl toward the second vector, while the thumb points toward the direction of the resulting vector. The cross product is commonly used in engineering and physics, particularly in studying torque, rotational motion, and magnetic forces. It is also useful in computer graphics for identifying surface orientation and lighting in three-dimensional objects. So this is the formula of the cross product. We have the vector A times the vector B. Next up, we are going to talk about the linear combination. A linear combination is created by multiplying vectors by scalars and then adding the resulting vectors all together. Scalars are ordinary numbers used to enlarge, reduce, or change vectors. For instance, if one vector is multiplied by 2 and another by 3, and then the results are added together, the final vector is called a linear combination. Linear combinations are important because they explain how vectors can be formed using other vectors. This concept is essential in vector spaces and in solving of equations. It also helps us understand how new vectors are generated from existing ones. In simple terms, linear combinations allow us to build new vectors from previously given vectors. So that will be all from linear combination. Next up is the linearly independent vectors. So vectors are linearly independent if none of the vectors can be represented as a combination of the others, meaning to say it's independent and there is nothing from the vectors, there is nothing that can be formed from the other because it's independent. This means every vector contributes unique information to the vector space. For example, the vectors angle bracket 1, 0 and angle bracket 0, 1 are linearly independent because neither vector can be produced from the other. The vectors 1 and 0 and 0, 1 are linearly independent because when we try to multiply this vector by 0, it gives us 0 and 0. But on the other hand, it's 0, 1. So therefore, it is linearly independent because there is no other vector that can be formed from these two vectors. So linear independence is important because it guarantees that each vector has its own distinct role in the vector space. These vectors are necessary when forming bases and analyzing the structure of vector spaces. Without linear independence, a set of vectors may contain repeated or unnecessary information. That will be all from our linearly independent vectors. Now moving on to linearly dependent vectors. So what is linearly dependent vectors? Most, pro- most probably when we say dependent, it is opposite from the independent. So a set of vectors is considered linearly dependent, rather, if one vector can be written as a linear combination of the other vectors in the set. So if linearly independent cannot be written as a linear combination of the other vectors in the set, then the dependent can be. Meaning to say we can form another vector from the linear combination of the other vectors in the set. This means that at least one vector depends on the others and does not provide new information. For example, if a vector can be obtained by multiplying or combining other vectors, then the vectors are linearly dependent. In simple terms, the set contains redundant vectors. Linearly dependent vectors are less efficient because some vectors are unnecessary. Since one vector can already be represented by others, it does not contribute anything additionally to the vector space. So, understanding linear dependence is important because it helps identify repeated or redundant information in a set of vectors. That is linearly dependent. Now, let us move on to the basis. So what is a basis? A basis is a collection of vectors that satisfies two conditions. First, the vectors must be linearly independent. Second, they must span the entire vector space. This means a basis describes the whole vector space without including redundant vectors. For example, the standard basis R squared is composed of the vectors angle bracket 1, 0 and angle bracket 0 and 1. Every vector in the space can be expressed uniquely using these basis vectors. Basis is important because it provides a simpler way of representing vectors and understanding vector spaces. And in linear algebra, finding a basis helps identify the minimum number of vectors needed to describe a vector space completely. That is all about the basis. Let us move on to the spanning set. So what is a spanning set? A spanning set is a group of vectors that can produce every vector in a vector space through linear combination. So if the basis has something to do with the linearly independent, then spanning set has also something to do with the linear combination with the linear dependent. For example, the vectors angle bracket 1, 0 and angle bracket 0 One span the vector rather space r squared because any vector in two-dimensional space can be expressed using combination of these vectors. Spanning sets are important because they show how an entire vector space can be generated. If a set of vectors cannot span a vector space, then there are vectors within that space that cannot be represented using the set. Understanding spanning sets helps determine whether a collection of vectors is sufficient to describe a vector space completely. So that is a spanning set. Let us move on to the dimension. Dimension refers to the number of vectors contained in a basis of a vector space. For example, r squared has dimension 2 because its basis consists of two vectors, while r cubed has dimensions 3 because its basis contains three vectors. Dimension tells us how many independent directions exist within a vector space. Spaces with higher dimensions allow greater complexity and are commonly used in areas such as engineering, data science, machine learning, and mathematics. And understanding dimension is important because it helps describe the size and structure of the vector spaces. That is dimension. Now to conclude, we are done with the topics from 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 the angle between two vectors, that product, the cross product, the linear combination, the linearly independent vectors, the linearly dependent vectors, the basis, the spanning set, dimension, and now to our conclusion. But before we move on to conclusion, vectors are very important to linear algebra because again, it is they can represent physical quantities such as force, displacement, acceleration, and motion. And to understand these vectors, it is essential because the concepts discussed are all connected to vector operations and vector spaces. So that's how important those topics that we discussed because they are all connected to vectors and we cannot fully understand the vectors without discussing the topics earlier. And now let us move on to our conclusion. To conclude, the concepts of dot product, angle between two vectors, cross product, linear combination, linearly independent vectors, spanning set, bases, and dimensions are all essential topics in linear algebra. Why? Because this concept help explain vector spaces, the relationship between vectors, and methods for solving mathematical problems. They are also widely applied in real-world fields such as physics, engineering, robotics, computer graphics, artificial intelligence, and machine learning. And again, linear algebra is an important area of mathematics because it provides tools for analyzing systems, interpreting data, and understanding multidimensional relationships. And that ends my discussion. Thank you very much for listening, and I hope this presentation helped you gain a better understanding of the fundamental concepts of linear algebra, specifically about the vectors. Again, vectors, they have both magnitude and direction. Thank you, and God bless.